Hi and welcome! Today we're gonna try to restore the legendary Asus P5A. It is a great ATX Super Socket 7 board based on the ALI Aladdin 5 chipset. This specific board is revision 1.06, which seems to be the last revision of this board. It comes with an ESS Solo 1 sound chip, which even though it's PCI based, it is quite compatible with DOS and doesn't sound too bad. This board, however, is in a pretty rough shape. Its previous owner had removed several components from it. The coils have been removed, an SMD capacitor seems to be missing from this part of the board, a couple of SMD parts have also been removed close to the audio chip, and even the USB receptacle is missing. The ISA slot is damaged and one of its pins is in pretty rough shape. There are also quite a few bent pins, but these can be easily fixed. One of the socket's mounts is partly broken, but it should be good enough for now. And finally, the back of the board has a few deep scratches that will most probably need repairing. Okay, let's try to replace the missing components. Let's start with the inductors. Luckily the board's seal screen shows the inductor values, 4 microhenries and 7 microhenries. I already have one ready-made 4.4 microhenry inductor, but I will need to make the other two myself. I used the online coil calculator at coil32.net to figure out how many turns each needed depending on the core used. Let's solder them on the board. Now let's add the missing SMD capacitor near the ISA slots. I had a look at some photos from the retro web and this looks like a fairly chunky ceramic capacitor. So I'm going to guess and use a 10 microfarad capacitor, which is the largest value I have. The capacitor near the audio chip also looks like a decoupling capacitor. I'm going to use this tantalum 10 microfarad capacitor as I couldn't find a second ceramic capacitor of this value in my parts. One side of this small capacitor doesn't look soldered to the board. It looks like the pad is lifted. A big blob of solder should do the job. Now let's try to fix the broken traces at the back. Yeah, this looks like a deep scratch. And once we zoom in, we can clearly see that there is a gap between the traces. Let's scrape off some of the clear coat. Now let's add some flux and thin the traces. The gap at the bottom trace seems to have been filled by the solder, so we only need to fix the top one. Now let's cut the wire with a blade. And let's clean the flags with some IPA. This damage is not deep and there seems to be continuity, but let's thin the exposed copper anyway. This one looks like it needs repair. This is my second attempt, as I could not get the wire to sit flat on the board surface the last time. Okay, now let's power on the board and measure the voltages at the CPU socket. The VCC2 CPU voltage is at 2.2 volts, which is correct. I guess the previous owner was using a K62 CPU. Now let's check VCC3. This is at 1.15 volts, which is not correct. I was expecting something close to 3.3 volts. So there must be something wrong with the voltage regulation circuit for the I/O power rail. Let's check which components are connected to the VCC3 pin. I have connected the other multimeter probe to my tweezers. These components close to the socket don't show continuity, so let's try the other ones behind the RAM sockets. And yeah, these are directly connected to the VCC3 pin. Here's a close-up of the circuit. This is a PWM regulator circuit based on the HIP6012 controller. These types of controllers were pretty common in boards of that period. According to the datasheet, some of the main components are the power MOSFET, which is this one on the board, the output coil, which is this one on the board, the Schottky diode that protects the transistors from the inductor kickback, and finally the feedback circuit that adjusts the output voltage, which in this board can be controlled with a couple of jumpers. Finally, I think the pull-down transistor is missing from the board. Since the voltage output for this regulator circuit is at 1.15 volts, then it is either that the power transistor is dead, or it's not getting turned on by the controller. So let's check the voltage at the transistor's gate. Yeah, the gate voltage is at 1.13 volts, same as its source voltage, so the transistor is not turning on at all. I checked the voltages on the oscilloscope, and none of the voltages of the controller show any signs of modulation. These controllers are supposed to be switching the transistor on and off at a frequency of around 100 kHz, but I couldn't see any such activity, so my assumption was that the controller was dead. But before I ordered a replacement, I wanted to check whether the board showed any signs of life. So I used the bench power supply to inject 3.3 volts to the source pin of the power transistor. And as you can see, the VCC3 pin at the socket shows 3.3 volts. Great! Off camera, I soldered the bench power supply leads to the back of the board to avoid any accidental short circuits. Let's power it on. And yeah, we're getting postcode, which means that the system is not dead. Now let's add a VGA card and try again. And yeah, it boots. Okay, while looking for replacement controllers, I found that the HIP6006 is more readily available and seems to be a pin-compatible part with slightly better voltage regulation, so I ordered that one instead. Okay, the replacement controller chip has arrived, so let's remove the old part. I covered the plastic parts with aluminum foil in an attempt to avoid melting too many parts. Well, the pin header next to the chip melted a bit, and the RAM slot has melted slightly, but nothing too serious. Let's clean the pads. And let's solder the new chip. Okay, so let's power on the board. VCC2 looks good, and VCC3 is at 1.44 volts. What a bummer. Well, that was a waste of time. So the controller chip must have been working all along, so something else must be wrong. Could it be that the power MOSFET is damaged and is somehow affecting the controller? Let's lift the gate and source pins and attach it to the chip tester. And according to the tester, the transistor looks good. At this point I was out of ideas, so I went back to the datasheet to look for clues. I went through all the pin descriptions and estimated what voltages are expected and compared them to the actual voltages on the board. And one pin seems to have the wrong voltage. It is the SS or soft start pin. When the controller powers up, this pin charges up an external capacitor, and once the capacitor's voltage reaches 4 volts, then it enables the controller's output. But on my board, this pin is at 0 volts, which means that the controller is thinking that it's in the soft start period, and therefore the output should remain disabled. But how can this happen? The only way is if the capacitor is shorted, but I tested mine and it measures close to the 0.1 microfarad value listed in the reference circuit. The only other alternative is for some other component being connected to the pin. And indeed, after a closer inspection of the board, I found another component connected to the SS pin. There is a small NMOS transistor that seems to be pulling down the SS pin. This looks wrong, but there is continuity between the source pin and ground, and the gate is driven by the 12-volt rail through a resistor. The only explanation I can come up with is that there may be some other component that is supposed to be pulling down the gate, but it's either damaged or there is some broken trace in between. Let's see what happens if we power on the board with the transistor removed. The SS pin is at 4.42 volts, which is above the 4 volt threshold value just as expected. The gate of the MOSFET is at 8.48 volts, which is a good value too, as it turns on the transistor. And the voltage at the output coil is at 3.55 volts, which is perfect. Finally, let's check VCC3 at the socket. And indeed, we are getting the same 3.55 volts. Let's insert the CPU, some RAM and a graphics card and check if the system posts. And yeah, it boots! There's still quite a bit of work to be done on this board. There's the missing SMD component near the audio chip, the missing USB receptacle, and the damaged ISA slot. And we also need to do some proper testing and run some games. But this video is already quite long, so you'll have to wait for part 2. Oh, and we didn't figure out what was going on with that transistor that was pulling down the SS pin of the power controller. If you have any ideas what it does or what could be driving it, please let me know in the comments. Okay, I hope you enjoyed this video, and as always, thanks for watching and goodbye.